The output characteristics is the graphical relation between the output current IC, versus the output voltage VCE for different levels of input current IB. For different levels of input current IB. The x-axis is for the output voltage VCE, this is in volts. The y-axis is for the output current IC, this is in milliamps. We already know IC is equal to beta times IB plus beta plus 1 ICBO. When base current, the input current, is equal to 0, this implies the collector current or the output current is equal to beta plus 1 times ICBO. So when base current or input current is equal to 0, the collector current is equal to beta plus 1 ICBO. So we have small current, which is equal to beta plus 1 times ICBO, or it is equal to ICEO when the base current IB is equal to 0 milliamps. This small current is the leakage current in the common emitter configuration, and you can clearly see this equation is independent of output voltage VCE. It clearly depends on the input current IB and the leakage current. The leakage current part is constant, so it depends on IB. This statement is not 100% true. I will explain why. First, we will complete the plot for different input currents. If we increase IB in equal interval, IC will also increase in equal interval. You can see when IB is equal to 0.1 milliamps, IC is equal to 5 milliamps. When IB is equal to 0.1 milliamps, IC is equal to 5 milliamps, and when IB is equal to 0.2 milliamps, IC is equal to 10 milliamps. When IB is equal to 0.2 milliamps, the collector current IC is equal to 10 milliamps. We can easily calculate the amplification factor, the current amplification factor beta. It is equal to delta IC divided by delta IB, small change in the collector current divided by small change in the base current. Delta IC is equal to 10 minus 5, and delta IB is equal to 0.2 minus 0.1. When you solve this, you will have 50. So beta, the current amplification factor, is equal to 50 for this characteristics. And you can see the slope is not equal to 0. The slope is not equal to 0 because IC also depends on VCE due to the early effect. We know VCE is equal to VCB plus VBE, and if we increase VCE, VCB will also increase, and when VCB increases, the effective width of the base decreases, and this will decrease the base current, and when base current decreases, the collector current will increase because more electrons emitted by the emitter will now collect to the collector. So collector current will increase and base current will decrease on increasing the output voltage VCE. So the collector current not only depends on the input current IB, it also depends on the output voltage VCE. Now we will solve one problem. This is very interesting problem, and in this problem, this region is region A, this region is region B, and this region here is region C. In column 1, we have region A, region B, and region C. In column 2, the first entity is saturation region, the second entity is cutoff region, and the third entity is active region. Now pause the video and try to match the correct options. I hope you have your answer. Now I will solve this problem. Region B is active region because in this region there is amplification of input signal. For example, when IB is equal to 0.2 milliamps, the output current IC is equal to 10 milliamps. So there is amplification of input signal in this region. That's why region B is active region. Region B is active region. Now I will find out what type of region is region A. For this I will consider the NPN transistor as two diodes connected back to back. This is the first diode and this is the second diode. If I consider the active mode of operation, then the collector current IC is having this direction and the base current IB is having this direction. This is when the transistor operates in the active mode, but we have to find out what type of region is region A. For this I will try to find out direction of collector current IC and direction of base current IB. You can see VCE is reversed. VCE is now minus VCE, and we already know VCE is equal to VCB plus VBE. VCE is negative, so we can say that VCB is equal to minus VCE minus VBE. So VCB is negative. VCB is the reverse bias potential, and now it is negative. This means VCB is now forward biasing potential, and the direction of collector current will now change. This direction is similar to the direction of arrow in the diode symbol. So this diode is also forward biased like this diode, and this happens in saturation region. So region A is saturation region. So the region in which VCE is negative is saturation region. But what about this region? This is also the part of saturation region, but VCE is not negative in this region. You can see VCE is greater than 0, but still this region is part of saturation region. I will explain why. You can see VCE is very small in this region. VCE is very small in this region, just greater than 0, and we have VCB equal to VCE minus VBE. When VCE is very small, VCB is negative. This means reverse biasing potential is not strong enough to reverse bias this diode, and the diode will remain forward biased. Because of this, this region is part of saturation region. Now we will find out what type of region is region C. In this region, you can see IB is less than 0. The base current is less than 0. So the direction of base current will now change, and the direction is opposite to the direction of arrow in the diode symbol. So this diode is now reverse biased, and you can see in this region VCE is much greater than 0. Because of this, VCB can easily reverse bias this diode. So this diode is also reverse biased. Both the diodes are reverse biased in region C, and this happens in cutoff region. So region C is cutoff region, and this is our answer. I hope you now have better understanding of active region, saturation region, and cutoff region. In the next lecture, I will explain common collector configuration of a transistor. So see you in the next one.